Okay, it's getting ready to happen.
Okay, sounds good.
Sorry.
All right. All right. Hi, everybody. My name's Sarah Blunt. I use she, her pronouns, and I'm really excited to talk to you about orbit fitting today. I want to first just thank Eric Nielsen, who taught me about orbit fitting and actually wrote all of the orbital elements on a whiteboard. And I can only assume that he's not available, and that's why you're having me talk here instead. Okay, so very briefly, I want to give you a sort of collage of some of the reasons you might want to fit orbits. The main point of this talk will not be about sort of motivation for orbit fitting. It will be about like how to actually fit orbits, so more like a tutorial. But I did want to give a little bit of motivation. So a couple of different things you can do. Many of the orbital elements are tracers of planet formation. So in particular, the eccentricity of a planet's orbit, its obliquity, like the angle of the orbital plane relative to the stellar spin axis, and also the semi-major axis. So all of these things can tell you about how planets form. Orbit fitting can also allow you to infer dynamical masses. So by dynamical masses, I mean a mass that's not dependent on the model you use for the planet's atmosphere. And then dynamical masses, in turn, can be used to constrain formation. And then also, as we just heard from Eileen, masses can actually be helpful for interpreting spectra. If you can place a nice constraint from a dynamical mass on your spectrum, it helps with the interpretation sometimes. Orbit fitting can also constrain a system's long-term behavior. You can constrain both the secular interactions, like averaged over many orbits, or n-body dynamics. And then finally, fitting orbits can also reveal additional companions in the system. And I've given a couple of different examples of ways that you might reveal additional companions through orbit fitting. All right, so what is orbit fitting? Orbit fitting is the process of using data to infer all possible orbits for an exoplanet. So for the majority of the talk, we're going to think about astrometry-only orbit fitting. So assuming you only have images of your exoplanet, and then at the end, we'll come back to incorporating other types of data. But so assume you have a sequence of images of your planet relative to your star taken at different times. You then canonically extract measurements. So we typically think about astrometry measurements as separation and position angle. So these are essentially polar coordinates for the relative distance between the planet and the star. And then orbit fitting itself is the process of turning these extracted measurements and their uncertainties into probability distributions over the orbital parameters that you're interested in. So things like semi-major axis and inclination of the orbit, things like that. So Bayesian orbit fitting specifically means using this equation. So we're trying to get the posterior, which is the probability of all of your orbital parameters given the data that you have. And the magic of Bayes' theorem is that you can compute this by multiplying the likelihood, which is the probability of your data given your orbital parameters, by a prior, the probability of just your orbital parameters with no prior information. So if we want the posterior, let's think about how we might get the likelihood and the prior. So first, the likelihood is given by this equation. So this is a Gaussian likelihood. And all of the variables here are the data points that you're trying to model, and then a model itself for how your orbital parameters predict the various astrometric points you have. And then all of your uncertainties on the individual points also come in at this point. So you could write your whole PhD on how to construct priors for orbital parameters, but I'll just say that the most common way to do this is to treat the prior as separable, meaning that you set an individual prior on each orbital element. So you set a prior on eccentricity based on what you believe about eccentricity without ever looking at the system. You multiply it by a prior on semi-major axis, etc. So the rest of the talk is about how to compute the model, and then you can just plug it into this formalism for computing the posterior. And a lot of this is taken from a chapter of my PhD thesis, so I go into a lot more detail there. You can refer to it if you're curious. All right, so I'm sorry in advance about all the equations. I feel like as I've gotten older, I've gotten less strict about not putting equations on slides, but I'm going to try to go through them slowly. So remember, our goal is to try to create a model of, given some set of orbital parameters, what are their predictions for what the relative position of the planet and the star is over time. So I'm not going to go through the derivation, but the way that you get these predictions for astrometry is by solving the two-body problem. So you use Newton's laws and you solve for the motion of two massive bodies over time. So this is what you get. So this is the model prediction, your relative right ascension and relative declination. So here I've switched to Cartesian coordinates for the relative position of the planet and the star. Then we've also got a bunch of orbital parameters here. So all of these things in green are characteristics of the system itself. So we've got pi as the parallax, a as the semi-major axis, e is the eccentricity or the shape of the orbit. And then we've also got a couple of angles here, the inclination, the argument of periastron, and the position angle of nodes. So all of these orient the orbit in space and then orient the orbit in space. And then we've also got a couple of these fun things called anomalies. We've got two flavors of anomalies, an eccentric anomaly here and a true anomaly. So these are functions of time. Okay, so let's talk a little bit more about the anomalies. The anomalies are things that relate time and position on the orbital path. So the first anomaly here, hold on. The first anomaly is called the mean anomaly, and this one is just directly proportional to time. So this one you don't have to do any special math to solve. The nice thing about mean anomaly is that it goes from 0 to 2 pi. It's like an angle. So it's not unbounded the way that time is. Then the next equation converts mean anomaly to eccentric anomaly, which is this big E, and uses the eccentricity in order to do that. So this is sort of the key thing that's hard in orbit fitting is solving this second equation, which is called Kepler's equation. Let me actually highlight all these for you. Yeah, so this is Kepler's equation. It's bad because it's hard to solve. But once you can solve the Kepler's equation, it's very helpful for predicting what your planet is going to do over time because mean anomaly is just going to increase linearly with time, whereas planets don't actually orbit like that. They orbit slower when they're farther away from their stars, and they orbit faster when they're closer to their stars. And so we need something that takes that into account. So the eccentric anomaly will not increase linearly with time. It will take into account the fact that your planet's moving at different rates depending on where it is in the orbit. So this diagram on the left shows you how all of these things are related. You have the star at one focus of your orbit here, and then the planet here. If you inscribe the whole orbit in a circle, the eccentric anomaly is the angle between this center and this projected position on the orbit at one point. And then another anomaly, which is just related by not a bad equation again to eccentric anomaly, is the true anomaly. So this is just another geometric sort of way to keep track of the fact that the planet's going to be moving at different rates throughout the orbit. So we've got two orbital parameters that make it into these equations, and then we've got three anomalies, which are all functions of time. So the next thing we have to worry about is how do you solve Kepler's equation? So in other words, given some set of times at which I want predictions for what my planet's going to do, how do I get those other anomalies that describe its motion through the orbit? Again, you could spend your whole career on this problem, and many, many people have. But I'll just give you a sort of common way to do this, which is the Newton-Raphson method. So essentially, you set Kepler's equation equal to 0, and then you solve for that 0 point. And this involves this sort of iterative process that I'm showing a GIF of from Wikipedia. So you start with an initial guess, you figure out based on where that guess intersects this function, you solve for its tangent line, and then there's some mathematical assurances you can make that if you do that repeatedly, you'll get closer and closer to the 0 of the function. All right, so a whirlwind tour. Here's everything together. We've got properties of the orbit. So these are orbital parameters that we're going to want to get posterior distributions of. And then we also have these intermediate variables, which are things we need to make the predictions. So all of these are functions of time, these anomalies. So there are 8 orbital parameters here: the parallax, the semi-major axis, the eccentricity, all of these 3 angles, tau, which places the planet at a particular location at one point in time, and then the orbital period itself. A note to keep in mind is that Kepler's third law is also a thing. It relates the period, the semi-major axis, and the total mass in the system. So this is also something that comes out of solving the two-body problem. So Kepler's third law means that you can only infer 2 out of 3 of these. So sometimes when people are doing orbit fits, they'll infer total mass and not period, or some other combination. So you can only get 2 out of the 3. Okay, so I've thrown a lot of equations at you, tried to give you a sense of like how you actually solve for these model predictions. I want to give you a little bit of a sense of how the orbital parameters actually affect the orbit. So we'll see if this movie works.
The relative orbit of an exoplanet.
It's so loud. I'm going to turn it a little bit down. Okay.
And its primary star is shown over 2 panels. The upper panel shows the orbit projected on the sky, with the primary star at the center, relative declination on the y-axis, and relative right ascension on the x-axis. The line of nodes is shown as a dotted vertical line intersecting the location of the primary at 0, 0. The orbit is circular, and the planet is shown moving at a uniform speed. The lower panel shows the stellar radial velocity curve as a function of time. Currently, the orbit is perfectly face-on, and the radial velocity is 0 at all times. The user increases the orbit's eccentricity, making the orbit more oblong. The planet's orbital speed is now fast near periastron and slow near apastron. The user now increases the orbit's inclination, rotating the orbit around the line of nodes. The orbit is no longer face-on, and the radial velocity curve has a sharp downtick near periastron and a gentle slope near apastron. Next, the user increases the orbit's position angle of nodes, big omega, rotating the position angle of nodes. This parameter does not affect the radial velocity curve. Next, the user increases the orbit's argument of periastron, rotating the orbit within the orbital plane. This changes the shape of the radial velocity curve, but its semi-amplitude remains constant. The user now toggles the inclination value again, changing the semi-amplitude of the radial velocity curve. Next, the user toggles the eccentricity to a large value, making the radial velocity curve appear very peaked near periastron. Finally, the user toggles the argument of periastron again, rotating the location of the periastron within the orbital plane.
All right, so hopefully that gives you a little bit of a sense of how all of these parameters actually affect the orbit. I hope it was worth it. It was terrible to listen to my own voice. Also a quick anti-advertisement for this diagram on Wikipedia. This diagram has caused so much trouble because the reference direction is off by 90 degrees to what we typically define in exoplanets. It's defined as the reference direction for what's typical for solar system studies. But yeah, so don't use that one. It's confusing. All right, so next I want to talk about some important degeneracies. And by degeneracies, I mean things that you can't learn from orbit fitting, particularly from astrometry-only orbit fitting. So I've just reproduced all of these equations that we need in order to solve the orbit, just for reference. So the first thing you might notice is that the individual component masses don't show up anywhere in here. The only mass that shows up is the total mass here. So you can't measure dynamical mass from relative astrometry alone. If you only take pictures of your planet and how it's moving, you're never going to be able to get individual component masses. Another important degeneracy is that parallax and semi-major axis are degenerate. So those are these guys in front here. And you can understand this by like these together give you the like apparent size of the orbit. So if the thing is farther away, but it's also got a larger semi-major axis, that appears exactly the same. So these two things are perfectly degenerate. This isn't quite as much of a problem because nowadays we typically have very good independent measurements of parallax from like the Gaia mission. So we can use those as like strict Bayesian priors, for example. Another important degeneracy has to do with 2 of the angles, the position angle of nodes and the argument of periastron. So position angle of nodes is the one that rotates the line of nodes in the plane of the sky. And then argument of periastron rotates the orbit within the orbital plane. So it just changes the location of where that periastron passage is. So these two equations are invariant to this transform, redefining argument of periastron as itself plus pi and position angle of nodes as itself minus pi. So that gives you this sort of characteristic symmetry in the two-dimensional space between these two angles. And you get this characteristic double peak in both of these when you're just fitting astrometry. A really nice tip is that this can be very helpful for assessing convergence of your MCMC models, because we know from this physical principle that these two things should be exactly the same. These two peaks should be exactly the same. But your MCMC won't show them as exactly the same until it's perfectly converged. One other thing I want to point out is that eccentricity and inclination and semi-major axis covariance is a really common feature of incomplete orbits. So I'm showing some excerpts from a corner plot of semi-major, the covariances between semi-major axis and inclination, eccentricity and inclination, and semi-major axis and eccentricity. So you can think for what this is showing is that for a smaller semi-major axis, we need a higher eccentricity and closer to a face-on orbit in order to intersect like a portion of the orbit. All right, so in the last couple minutes, I want to talk to you a little bit about incorporating other data types. So far, we've only thought about modeling the relative position of a planet and its star. Luckily, it's relatively straightforward to add additional information into the Bayesian model. We're predicting. We just need a new method of predicting what the thing is going to do, how the orbital parameters are going to affect that particular data type. So let's now add in radial velocity points. So this is a really nice little GIF showing you how the radial velocity method works. You have a planet and a star orbiting their common center of mass, and that causes the star's speed to appear to change over time, something that you can measure from the Doppler shift of the star's lines. So we can modify our model to be able to predict the radial velocity curve over time. I've got two different predictions here. One for stellar radial velocities, so if the spectrum comes from the star directly, and one for the planetary radial velocity, if the spectrum comes from the planet itself. These are very similar, but you can see there are a couple of small differences. One important thing to point out is that all of a sudden the individual masses show up in these equations. So the critical takeaway here is that if you have radial velocities, you can constrain individual component masses. But a common point of confusion is that if you have a radial velocity measurement of a planet, you actually can't measure the planet's dynamical mass. The thing that you get a measurement of is the star's dynamical mass, which isn't quite as interesting because the star's dynamical mass and the total mass of the system are usually pretty much the same. So we're not as interested in measuring dynamical masses of stars. We're really interested in measuring dynamical masses of planets. Planetary radial velocities, however, are useful for a whole host of other things. They also constrain other parameters like eccentricity and semi-major axis, et cetera. All right. Now let's talk about another additional data type, which is absolute astrometry. So absolute astrometry is this idea of very precisely measuring a star's position over time. And in particular, the combination of absolute astrometric measurements from Hipparcos and Gaia has become really popular in the past couple of years. So here's a really nice diagram of how this works. If you have a couple of measurements of a star's position relative to the barycenter over the Hipparcos baseline, and then a couple more measurements over the Gaia baseline, you get sort of three proper motion vectors, one that represents the star's motion over the Hipparcos baseline, one that represents it over the Gaia baseline, and one that connects them together. And so these absolute astrometric measurements you can also incorporate into your model. Something to keep in mind that I think is important is that where absolute astrometry comes from. So this is a nice little three-panel diagram that shows you if you measure a bunch of stars using something like Gaia or Hipparcos, you come back several times and you can measure their proper motion vectors, like how they're moving through the sky, and also their parallactic ellipses. So they make these little curly cues. That's a signature of how far away the system is, and the Earth's revolution around the sun. So you model all of these things jointly. You make a really giant model that figures out what the best individual parameters are. So you're not for relative astrometry, you're just tracking the planet's location relative to its star over time. But for absolute astrometry, you're measuring the position of every star relative to every other star. So it's a very complicated thing to do. All right, so now let's add this absolute astrometric model. Let's create a model for the absolute astrometry. So there's a lot of different ways to do this, so I'm not going to go into it in a ton of detail, but the general way to do it is you model your absolute right ascension and declination position of your star over time as a sum of the parallax motion from the revolution of the Earth around the sun, plus the proper motion of that particular star through the galaxy, plus the delta RA and delta dec that we derived a couple slides ago. So I've just got them here very small as just a reminder of what I'm talking about. But then you multiply that by the ratio of the planet mass over the total mass. So importantly, again, the individual component masses are entering into these equations. So the critical takeaway here is that absolute astrometry can also constrain your planet mass. So this is probably the main reason why absolute astrometry and radial velocities are important to be able to combine with relative astrometry, because it allows you to constrain dynamical masses, which is something that astrometry cannot do. Relative astrometry can't do by itself. All right. So the very last thing I want to leave you with is that orbit fitting is a really big field, and I didn't have enough time to talk about everything that's going on in the field. So I wanted to point out a couple more things that I thought were really interesting. First, you can think about adding multi-planet effects into the model. So far I've been telling you about pure Keplerian orbits, but there's a lot of stuff you can do to start thinking about the interactions between planets. You can also think about systematic errors, particularly in radial velocities and absolute astrometry. And there's a lot of work in both of those fields to understand the non-Keplerian components of both of these types of measurements. Another really interesting thing to think about is deconfusion, which I think is going to become much more important in the next couple of years with the launch of Roman. So this is the idea that if you have a radial velocity measurements of a system with multiple planets in it, how do you know which radial velocity signal corresponds to which dot of light you see when you point your telescope at it for the first time? And another, I think, interesting and important thing to point out is reducing bias in Bayesian posteriors on orbital parameters. And there's been a lot of really interesting work in recent years by Kelly O'Neill and Greg Martinez. And then I also just wanted to point out some open source orbit fitting codes that are used by exoplanet imagers. This is, I don't think, an exhaustive list, but yeah, so I linked to their docs, and also wanted to point out that this list is probably going to expand in the advance of the new release of Gaia time series data. So definitely keep an eye out for new orbit fitting codes as well. All right, happy to take questions.
Thank you so much for this excellent talk. So if there is any question, we have a few minutes. Yep.
Hi, Sarah. Thanks for the great talk. Marv and Jikji, Arizona State University. So I just kind of want to ask, where do you think the field of orbit fitting will take us once like Gaia DR4 comes out? Like, do you see anything new happening in the way that we fit orbits, or anything new that we could learn from the new data release?
Yeah, great question. I'm super excited for DR4. I think it's going to totally revolutionize the field. I think one thing that will DR4 is going to be sensitive to planets that are at sort of intermediate separations. to what we like typically look at with direct imaging. And so I think that'll open up a sort of, it'll expand the parameter space of planets that we, you know, it'll expand the parameter space of planets that we're interested in, that we know about. And then I think it'll also open up really interesting opportunities for follow-up with direct imaging. So we might be able to we'll discover these planets with DR4 and then follow them up with direct imaging and get dynamical masses and stuff like that. But then, I think there's also a whole host of questions about like, how do we best fit DR4 data, which I think the field is going to have to explore in the next couple of years as well. So I don't know if I have a great answer to that question other than it's definitely a thing we're going to think about. Actually, yes,
Microphone is back.
Okay, hi. Very nice talk. I'm Zhe Cheng from Tsinghua University. Yeah, I have a question about the Theoinus elements. I heard that the Theoinus elements are widely used in astrometry, absolute astrometry fitting. So I just wonder, in the this relative orbital fitting, is this element also widely used? So, and why or why not? Yeah, thank you.
Yeah, good question. So the Thiel-Innes elements are a different parameterized. So let me go back to these. Here. So this parameterization that I taught you is called the Campbell orbital elements, and Thiel-Innes is another parameterization. And one really nice thing about the Thiel-Innes elements is that they're 4 of these parameters are linear, which means that you don't have to separately fit for them in like an MCMC setting. And I think in Gaia DR4, the team like uses the Thiel-Innes elements, I know, and part of the reason is that it's very fast to do that. So it's a lot more computationally efficient. I think we're still sort of in direct imaging, we're really concerned about the influence of priors, and it's sort of not as straightforward to set priors on the Thiel-Innes elements and then convert those to the Campbell elements. So historically, that's I think why we've been more leaning towards the Campbell elements, but I think that might change as we get better at math. Great question.
Any other question? Okay, so let's thanks again, Sarah.